Hello everyone, we are Team 3. We are currently in Seminar 4 and today we will present our project. The members of this team are Eric, Eduardo, and Rene.
Without a doubt, we've come a long way through these four seminars. Between successes and failures, we've embraced the methodology proposed by Ulrich and Eppinger for new product development. Each of these seminars has provided us with lessons and paradigm shifts that have allowed us to conceptualize and refine our concept, transforming an initial idea into something much more solid and meaningful. Throughout this presentation, we will address our interest in the selected opportunity as well as a brief summary of the results of the seminars that allowed us to arrive at our final concept. In Mexican households with an average of 4 inhabitants, it is estimated that around 150 liters of water are wasted per day due to bad habits, such as leaving the water running while waiting in the shower or during activities such as washing dishes and clothes. According to the EPA, approximately 20% of the water used in a shower is wasted while the user waits for it to reach the proper temperature. Since an average shower consumes about 65 liters of water, this 20% is equivalent to about 13 liters per shower. In a household of 4 people, this waste could add up to almost 19,000 liters of water per year. During Seminar 1, and based on the methodology described in the book on design and development by Ulrich and Eppinger, we were able to establish the mission of our product, which has guided us throughout our development. Modernization of the shower system for homes, for installation in the exposed piping of the existing shower system, reducing the time it takes for hot water to flow when opening the faucet to start the shower, reducing water consumption, and offering an efficient, adjustable, and comfortable flow. We have kept this description in mind throughout the seminars. However, as we will see throughout this presentation, some of our design decisions have slightly deviated from the initial scope.
In Seminar 2, we defined the final list of needs by assigning each one a level of importance. We also generated the metrics applicable to these needs, for which it was necessary to conduct a study to determine which metrics would be appropriate to validate and certify our product. At this stage, we conducted research on existing products in the market that could be direct competitors to our project. For this reason, we initially sought to avoid biases by carrying out in-depth research considering different features, functionalities, prices, etc. In this stage, we also compared each product with a list of metrics and needs in order to determine which product was the best in the market and to establish a reference point for our own product. It is important to mention that we created a spider chart where we could visually observe that product number 6 ranked as the best on the market. In the patent search process, we followed the instructions shared with us by the professors. First, we described the invention. Then we identified the relevant classifications, reviewed the definitions of these classifications, and subsequently carried out the process of searching, selecting, reviewing, and referencing using the CPC. We also conducted the search in Google Patents and Espacionet. In the search, we identified very interesting patents, and one of them described our problem: avoid wasting cold water before hot water comes out. This process helped us identify both positive and negative aspects, and carrying out the development allowed us to identify opportunities to improve existing developments, avoid risks detected in the developed patents, protect our innovation, gain a visualization of the problems being solved, and most importantly, obtain an overview of how we can meet our clients' needs. Once we obtain the target specifications and define the marginal and ideal values, we proceeded to carry out the clarify the problem stage. This process was a challenge for us, as it was not very simple to perform with our product. The problem was decomposed into subproblems in such a way that we carried out the three indicated decompositions: functional decomposition, user sequence decomposition, key user needs decomposition. At the end of this process, we obtained the 5 critical subproblems that would be addressed. This process helped us to visualize the complete product, design and develop each function independently, prioritize functionalities, and establish the logic in the user sequence.
These are the critical subproblems we've identified and will address throughout Seminar 3. We met as a team to conduct an internal search, using our individual and group knowledge of the project to generate ideas. It's important to mention that we sought to be as creative as possible during our brainstorming sessions, so we tried to be as thorough and creative as possible to tailor the information to each subproblem. During this third stage of seminar, an internal search was carried out using different strategies to identify ideas such as creative role-playing. Some ideas generated in the stage are presented. During this stage, intelligent designs incorporating motion sensors and different water mixers were explored. The external search was carried out in order to explore what already exists in the market or is in development, such as patents to improve our concept, such as the method to empty our system of water over its circulation.
In the first stage of Seminar 4, the multi-voting process was carried out within the team to select the final concept. We should highlight that the winner of this multi-voting was different from the last options in Seminar 3. This was because the previous concepts did not have the necessary potential to move forward. It is important to mention that the team carried out an evaluation of Concept 7, which had been selected in Seminar 3. By using the mentioned process and analyzing the professors' and thesis advisors' comments, Concept 14 was selected, which is a system that has a stored water tank, recirculates the water, and uses a thermostatic mixing valve with infrared sensors and automatic pressure pumps to maintain pressure. It is important to note that this concept was later improved. The selected concept was Concept 14, which already includes a water storage tank to collect the cold water standing in the hot water pipe. This cold water is later pumped to a mixer to recovery and ensure that the tank is always empty and available to temporarily store the cold water from the hot water pipe. It is important to mention that in this process, we also carried out calculations for the tank size, the pump's energy consumption, and the battery's energy consumption and capacity. The strategic decision to focus on the C segment is based on a precise alignment between the characteristics of this market and the value proposition of our product. Therefore, it was decided to target this segment for the following reasons: purchasing power and willingness to invest in added value, appreciation for quality, durability, and design, interest in innovation, sustainability, and efficiency. According to NAD, a person in the C class earns a monthly income ranging from 35,000 to 55,000 pesos. In summary, the C market is not only economically viable for a proposed price, but its values and expectations regarding quality, design, and innovation are a direct reflection of the core attributes of our product. This ensures a strong connection and a high adoption rate. In this stage of concept testing, we selected the survey format and decided to conduct it via video conference. Therefore, we considered the possibility of biases and how to mitigate them. For this reason, we decided to create a concept in SolidWorks and present the generated concept to the interviewees. Afterward, we developed the plan for the video conference interviews. It is important to mention that these interviews allowed us to gain deeper insight into users' reactions, and their feedback provided us with significant value. In the following report, we decided to create a YouTube video about the operation of our product and share it with the interviewees. Through Google Forms, we generated a series of questions to obtain more information about their feedback on the concept. It is important to mention that the reception of the video was very positive, and the feedback provided helped us measure their responses. Afterward, we measured the users' responses, obtaining very interesting insights such as genuine interest in the product, attraction and interest in water savings, some concerns about the complexity, size, and possible cost of the system, and most importantly, their willingness to make a change to their current system due to the severe water shortage in Mexico and their interest in our system. Therefore, we presented the data and graphs, and in a more visual way, we were able to see that the greatest interest lies in avoiding water waste. Moreover, even though the price could be high, it would be compensated by the water savings given the current water crisis. Finally, these results represented an opportunity for improvement for us, where in the next steps we would place greater focus. Here are some examples: position and size of the battery, water consumption, mounting hardware to the bathroom wall, adding a second pressure sensor for the hot water line, temp level measurement, etc.
During the process of developing the architecture of our shower system, we went through a series of stages that not only allowed us to technically structure our design, but also forced us to deeply reflect on our decisions, correct errors, and learn to interpret the feedback we received. The first step was creating the diagram, where we represented the flows of materials, energy force, and signals. This forced us to understand the system from a functional perspective, rather than simply considering it as a set of components. From there, creating the diagram where the elements were grouped into functional subsystems allowed us to more clearly visualize the internal relationships, optimize the system's organization, and anticipate future tasks such as assembly, maintenance, and validation. As a fundamental part of the development of our system, a detailed bill of materials was created. This list not only identifies each of the components required for proper operation, but also allows for precise control of costs, technical compatibility, and manufacturability. The importance of this list lies in the selection of materials based on the following criteria: thermal and corrosion resistance, mechanical compatibility between components, availability in the domestic market, cost benefit ratio, overall material efficiency. This section presents the initial CAD models of our product concept. It should be noted that these designs represent an early stage of the engineering process, which was subject to revisions and modifications based on feedback from consultants. We decided to include this version of the design to document the evolution of the project. The resulting updates and changes will be presented in the following slides. At this seminar, we conducted a second phase of competitive benchmarking, a fundamental process for validating our product concept. This analysis was conducted with a new approach, as the evolution of our concept required a re-evaluation of the competition. The methodology remained focused on key user needs and established technical metrics, allowing us to update our value proposition and ensure its competitiveness in the market. This process allows us to know our competition's prices and characteristics, as well as how they try to meet user needs.
Operating description. The system recovers stagnant water from the hot water pipe until it reaches the system's program temperature, 40 degrees Celsius. It allows showering to be partially automated, avoiding constant adjustments. These two main actions minimize water consumption during showering. The exposed elements of the system are the following: the electric charging center, the interaction components, a main access to the cabinet, connections with flexible hoses for its installation, and a shower head is also incorporated. The system has the following components as a user interface: a power button to energize the system, an electric charging center for recharging energy, a manual operation button, and another to recover water from the hot water pipe, a thermostatic valve with a temperature selection handle, a presence sensor, and LED indicators that allow viewing system status changes. Below are the internal components: three solenoid valves for internal water flow control. The first is used to divert water to the tank. The second supplies hot water to the thermostatic valve, and the third releases the mixed flow. Two temperature sensors that monitor the different temperatures of the water in its path. The first monitors the change in temperature of the water coming from the heater, and the second monitors the mixed water. A presence sensor that, together with the manual button, activates the water mixing solenoid valve. A tank for storing recovered water. As a precaution, the tank has an upper cavity that allows overflow in case the level sensor fails. An internal pipe that connects to the existing hot water pipe. An internal pipe that connects to the existing cold water pipe. A water recovery pump that allows the stored water to be integrated into the cold water flow of the system. A level sensor that allows monitoring the water level inside the tank. The electronic control card to control the system logic. A battery that supplies power to the different elements of the system. Before energizing the system, it is preferable for the user to select the desired temperature using the thermostatic valve handle. This allows the valve to be prepared for mixing the water through mechanical thermal reactions. It should be noted that at this point, the remaining water in the hot water pipe is at room temperature. After selecting the temperature, the system must be energized. Red LED light is on. At this point, all valves remain closed. The purge button must be pressed. This allows the solenoid valve 1 to open and allows the passage of water to the recovery tank. At this moment, the yellow LED is activated and flashes. During the flow of water, temperature sensor 1 detects the temperature change. The system is equipped with an ultrasonic sensor to measure the water level in the tank. This allows the system to determine how much water is stored. This sensor provides feedback to the water pump to determine when to stop. As the stagnant water is purged from the hot water pipe, it is collected in the system tank. Using the level sensor, it is possible to determine the amount of water recovered. During the water flow, the temperature sensor 1 senses the change in temperature. And when reaching a temperature of 40 degrees Celsius, 104 degrees Fahrenheit, solenoid valve 1 closes. This action allows hot water to flow to solenoid valve 2, and the yellow LED stops flashing and remains fully illuminated. At this point, the user is recommended to press the manual activation button. This will open valves 2 and 3. After this, you must wait at least 5 seconds. This same action can be performed by bringing your hand close to the sensor and leaving it there for 5 seconds. When solenoid valves 2 and 3 are opened, water is allowed to pass through the thermostatic valve, and the stagnant water in the tube that reaches the shower head is released. The green LED will only light up when the system distributes water to the shower head. From this point onwards, the opening and closing of solenoid valves 2 and 3 will be activated by the presence sensor. LED light turns on. The system normally operates as a commercial thermostatic mixer does. To integrate the recovered water, the system incorporates a water pump to extract water from the tank. The water pump is activated automatically and intermittently throughout the operation of the system, which allows the recovered water to be integrated into the cold water line. Remember that the level sensor provides feedback on the operation of the water pump. The water pump capacity and level sensor measurements cause the water pump to stop when the tank is empty in approximately 1.5 minutes. The user continues with his shower activity by activating the system using the proximity sensor. And when finished, you must turn off the system. This de-energizes the solenoid valves and closes them until their next use. Using the system with intermittent shutoffs and initial water recovery reduces consumption from 83.12 liters to 38.12 liters per shower, generating a theoretical saving of 45 liters. In a family of 4 people, this represents an estimated annual saving of 65,700 liters, equivalent to 17,356 gallons. With an average system consumption of 4.57 watt-hour per shower, the 240 watt-hour battery allows for up to 52 showers before needing to be recharged. For a family of 4, the battery offers an estimated runtime of 13.1 days before needing to be recharged.
Conclusions. This seminar was a very important challenge for us, where we decided to focus on ensuring the functionality of the concept and fulfilling our mission statement, which is to reduce water waste while reaching the desired temperature. We agreed that an important next step will be to calculate the manufacturing and commercialization costs to ensure the success of our concept. It is important to mention that, as a team, we have very positive expectations for our product. We appreciate the support and guidance provided by our professors and advisors to carry out the product development process in the best possible way. For us, selecting such a complex product was a great challenge. However, this choice was made by following the process outlined in the book and with the support of our professors. Currently, water scarcity is a critical issue in Mexico, and for this reason, important actions are required to ensure responsible consumption and to raise awareness among Mexicans to avoid waste. We want to thank all our professors and advisors for guiding us, for their patience, their orientation, and for listening to us. Without a doubt, we are very satisfied with having chosen this master's program, and we are deeply grateful for having learned how to develop and launch a product. Thank you all, and may God bless you.